Great. Thanks so much, Claire, for the introduction. I'm absolutely delighted to be here with you, and I've picked a topic to talk about, which I've entitled The Quiet AI Revolution, in contrast to other bits of AI which are rather noisier. So there's no risk from the sort of AI I'm going to talk about of it taking over the world. We're not going to talk about people being fired from high-profile companies moving to Microsoft. It's a rather quieter but rather deeper story, I think. And I'm going to unpack this revolution through this lecture. I do work at Microsoft Research, but I have to sort of make the statement that I'll not be talking about my work there or the views of Microsoft Research in this talk. In fact, I'll be talking about mainly other people's work with, noting up as we go along some connections to things which are going on in my own research group. Okay, so I want to start by motivating why you should all be interested in weather prediction. And there are a couple of different motivations. The first thing is severe weather, like that depicted on the slide here, kills, unfortunately, about 40 or 50,000 people each and every year. And that number has gone up by half since 1950 due to climate change. It costs every one of you in the audience, on average, about £50 a year, the damage caused by that extreme weather. That's everyone actually across the entire globe. For some people, it'll obviously be a lot more than that. It's really important we develop better predictive systems for warning us about severe weather in order to mitigate those incidents. It's also critical for many industries, if you think of shipping or aviation, for predicting energy, how much energy we're going to get out of renewables in the next week. We need weather prediction systems. Insurance, agriculture, etc. They all rely on weather prediction systems. So what I'm going to do to start this talk is I'm just going to tell you a little bit about the history of weather prediction. And I'm going to start with a chap that's quite well known called Lewis Fry Richardson. So Lewis Fry Richardson actually was an undergraduate at Cambridge. I get my obligatory sort of somewhat nepotistic reference this time to King's College. They win the lottery this time. He's at King's College and he studied natural sciences. He may well, have sat similar lectures on chemistry in a lecture room much like this. And way back in 1915, he decided to carry out the first forecast of weather by simulating by pen and paper the underlying equations of weather. And he took the approach of discretizing the equations both in time and in space, breaking up the local area into little grid cells and breaking up time into little segments. And he made a forecast of what would happen 6 hours ahead at the current location he was in. That forecast took him 6 weeks to complete. So it wasn't very useful as an operational forecast, but he laid down the methodology, the mathematical methodology that was required to carry out that forecast. And he went on to write a book in 1922 called The Forecast Factory, when he imagined what it would take to scale up those exact same procedures that he used in order to make forecasts for the entire globe on a regular basis, say an hourly basis. And in his imagined forecast factory, there would sit 64,000 people calculating away the same equations that took him 6 weeks to calculate, and they would pass notes to one another because for me to forecast the weather in my little grid cell, I need to know what the people next to me, what their predictions for the weather are going to be. And he imagined a conductor at the center that would coordinate these 64,000 workers in this giant circular hall, and he would take the predictions from each one of these people and put them on this giant map in the ceiling, which is depicted in this image here. And just because anything you can do, I can do meta, this is in fact an output of generative AI based on the text from Lewis Fry Richardson's book depicting his forecast factory. Okay, so that was 1922, and since then, a lot of things have happened. In particular, in the 1950s, we had computing come in, and supercomputers for the first time started to be built, and they allowed Fry Robinson's vision to start to be actually put into operation. So we could simulate the same equations that his forecast factory were going to simulate, but now in a digital system, and this cut down the time it took to make forecasts dramatically. And by and large, this way of predicting the weather, called numerical weather prediction, has persisted for the following 70 years until this year. So this year, for the first time, a new breed of weather prediction systems has started to be deployed operationally in anger. And that's what this talk is going to be about. These new systems operate in an entirely different fashion. They take weather data, some of it generated by numerical weather prediction systems, and they train on it. And that training procedure we're going to talk about in some detail is going to be quite expensive and is going to involve a big system. But once they're trained, it's going to be possible to do what the supercomputer is doing on a simple desktop machine. So this is 1,000 or 10,000 times faster, or 1,000 or 10,000 times less computing infrastructure required to actually carry out these predictions. So this is what stands to have a huge impact on weather forecasting. It can lead to more accurate predictions. It can lead to finer resolution predictions, both in time and in space. And it's fair to say there's going to be some time over the next few years where we figure out exactly how and in what ways it's transformative. And I'm going to talk through some of those issues in the next 45 minutes or so. Okay, before we do that, let's just zoom in a bit more detail of what has happened in the last few years in this space to see how quickly this sort of revolution in AI weather prediction has happened. So I want to rewind back to 2020, and this is a paper I've taken from the Royal Society's Philosophical Transactions A. So this is a published paper, and the published paper aimed to sort of scope out how vulnerable different bits of the weather prediction pipeline were to an insurgent AI-based approach. And in particular, they say this sort of generous statement here. I think at the time they thought this was generous towards AI. They say, it is not inconceivable that numerical weather models may one day become obsolete. That's the sort of weather models I was talking about in the previous slide that Robinson sort of introduced to us. But a number of fundamental breakthroughs are required before this goal comes in reach. And if you asked a typical person in the field, a meteorologist, say, they would have said in 2020 that this may take decades, essentially, for these breakthroughs to be ported into real systems. Okay, fast forward into May of this year, and in Nature is a paper called Accurate Medium-Range Global Weather Forecasting with 3D Neural Networks. This is a paper that we're going to talk about a lot in today's lecture. I'm going to really unpack what's going on in this paper. It was by Huawei, and they developed a system called Pangu Weather, and what caused everyone to sit up and take notice was that for the first time, they had managed to produce a machine learning space system that was competitive with current best numerical weather prediction algorithms, the sort of traditional algorithms I was talking about before. And as they say, this breakthrough came much, much earlier than expected. People expected this to happen in 2030 or maybe even beyond, but it was happening in May of this year. And just to prove how topical this topic is, last week, Google DeepMind's model was published. You may have seen this to much celebration in the press. And Google went a little bit further than this paper. I'd say the main breakthroughs are actually made in this paper before, this paper by Huawei called Pangu. They sort of nipped in and scooped DeepMind. But DeepMind's system is a little bit better than Huawei's, and for the first time it actually outperforms conventional weather forecasting. And we'll unpack in exactly what sense that's meant. I should say there's a lot of hubris around these press statements that come out. And there will be at least 3 or 4 things that I'll pick out from the papers where the statements that you read in things like the Financial Times and the press aren't exactly true. So I'll hopefully lift the lid on exactly what has and what remains to be sort of solved in this space. Okay, great. So that's sort of the context of the last year, topical right up to last week. And the title of this lecture was based on an article by Stephen Belcher. Stephen Belcher is in charge of the Met Office, and he wrote a really nice piece called "A Quiet AI Revolution is Taking Place in Weather Forecasting." And his focus was not only had the potential to improve numerical weather prediction, it also has the potential to reduce carbon emissions, because these huge supercomputers involving thousands of CPUs, which are required to carry out numerical weather prediction, could be replicated on cheaper hardware like desktop computers, and therefore would reduce the immense carbon and compute costs associated with it. Billions of pounds a year are spent on the compute costs associated with numerical weather prediction. Okay, so this is the scene. It's all been set. We're going to sort of debunk some of the papers and sort of lift the lid and try and understand a bit about what's going on, what you should be excited about, what you should take with a healthy degree of skepticism. In order to do this, in order to bring you with me on this journey, I need to explain a little bit about the background to numerical weather prediction and forecasting. And so we're going to spend the next 20 minutes sort of doing new sort of weather forecasting 101. Okay? Okay, great. And the first thing we need to talk about is the fact that there are actually lots of different types of weather forecast, depending on how far you want to predict into the future. There's not just one type of forecast, there's actually a bunch of them. And the papers that we're looking at and the breakthroughs that have happened to just one of these types of forecasts. Okay, so look, what are the other types? Well, to start with, if you're interested in forecasting a few minutes into the future, say 15 minutes into the future, or maybe just a handful of hours, you're in the game of what's called nowcasting. So this might be the sort of forecast you look at when you've got a football match in a couple hours' time and you want to figure out, is it going to be raining and windy during the football match, or will I get drenched on the way to work this morning in the next 15 minutes? Often people are very focused on predicting things like precipitation and whether it's going to rain or not in this type of forecast. So that's nowcasting. If you move the forecast duration up to forecasting several days into the future, or to forecasting maybe a couple of weeks into the future, you're into the regime of what's called medium range weather forecasting. And if you go further up to months or years, you're into what's called subseasonal forecasting. Are my crops going to fail? Are we going to have floods or droughts? And then right up to very long time scales, you get into what's called seasonal or climatic forecasting. So this is like the broad spectrum of timescales which are going on in forecasts. And the different types of timescale require different types of solutions. If you are in this scale down here, where you're predicting minutes or hours into the future, the nowcasting timescale, then you can build local models in order to do this. You don't need to simulate weather on the whole globe, because weather on the other side of the globe doesn't have enough time to come around and influence the weather that's 15 minutes ahead of you at your particular location and time. So you can just build a local area and simulate in Richardson's style over this small local area of the globe. What's more, the variables are more deterministic. They're easier to predict. Things like temperature are actually very easy to predict 15 minutes or a few hours ahead. You don't need to return your predictions with some uncertainties. You can just say, I think this is what's going to happen, and make one single forecast. The weather is mainly driven by the dynamics of the atmosphere on these sorts of timescales, which have time constants which are of the order of hours or days. Okay, and as we move across here to medium range weather forecasting, then things start to look more different and a bit more challenging. So first thing is that we now need to have to build global models, because the weather where I'm looking at 2 weeks' time will depend on what the weather's doing on the other side of the world. And so rather than focusing on a little patch and doing Richardson's calculations over that local area, I now need to build a model which is going to go all the way around the globe, because it's relevant for how the weather is going to move around the sphere. And if we go out to these longer timescales out here to seasonal and climatic or subseasonal forecasting, then we're in a regime where we cannot be absolutely certain what the weather is going to do at any one point in time, and we need to start outputting a range of possible forecasts for what's going on, which are consistent with the current weather at this time point, i.e. we need to build uncertainty in our forecasts and they become stochastic. And that transition from deterministic forecasts to forecasts with uncertainty happens somewhere around the 2-week mark, maybe a week to 2 weeks. Things start to become non-deterministic and you need to include uncertainty in your estimates, right in the middle of this sort of medium-range weather forecasting regime. Great. And I should say, at these very long time scales here, as we move out to months and definitely to years, we move away from the dynamics of the atmosphere being the time constants which are important to the dynamics instead of the ocean, things like El Nino and the Southern Oscillation. These are the things which have time constants over several years and allows us to have predictive power in order to predict things like climate. Okay, so these are the ranges of forecasts that are out there. And the papers that we're looking at and the quiet revolution that we're going to consider is going to be happening in the middle here, to this medium range weather forecasting regime. So you're forecasting maybe 6 hours to 2 weeks into the future, that kind of range. And you'll see this on the plots we look at later. I should say there's a lot of work in AI and these other areas and statistics, a lot of good work. Nowcasting, for instance, has involved AI-based methods for a long time, but that's not something we're going to talk about in the talk today. Okay, so let's take a little bit of time to talk through how medium-range weather forecasting currently works. And here it will become apparent that it's not true that AI has revolutionized all of medium-range weather forecasting. There are large bits of the pipeline which remain to be solved. Okay, so let's imagine we start here at the current time, and at that time point we have information about the current state of the atmosphere all around the world. I'll talk about where this comes from in a second, but let's imagine it's given to us to start with. What we're going to do is we're going to make a forecast, a time delta into the future, where delta might be a day or a couple of days, or it might be 6 hours. And that forecast, like I said, this is the thing which Richardson computed, involves simulating lots of equations, differential equations. And here, just to give you an example of what those differential equations looks like, I've taken a page out of the European Centre for Medium-Term Weather Forecasting's handbook, which describes their model for producing this forecast, their numerical weather prediction model. This document is 40 pages long. All the equations across those 40 pages have to be implemented in code and run on a supercomputer. And what's more, they're run with a time step of about 12 minutes. So every 12 minutes, they update the current picture of the weather state across the world. So it's an incredibly computationally intensive thing to run. And they run with a grid across the world, which is of the order of several kilometers across the world. So every square, say 3 kilometers, is a grid cell in this model. And that's why it's so expensive. Okay, so you run that forward to make a prediction. And then, of course, in the next hour, we've observed lots of information about the weather. We've observed planes. Planes are flying around measuring pressure at different heights through the atmosphere. There are weather balloons collecting data about weather, sometimes in places where they shouldn't be. Sometimes they're not even weather balloons. And we have satellites up in the atmosphere collecting lots of data. In fact, most of this observational data we have comes from arrays of satellites around the world. Ships are recording temperatures as they go across the seas to get information about the weather across the oceans. And we also have lots of weather stations. Here's one in the Antarctica. Okay, and this information needs to then be combined with the forecast at that time point in order to better understand what the atmosphere is doing at time t plus delta. So you forecast forward, and then you collect observations, and periodically you have to update these forecasts to include the observations to make it a bit of a better representation about the atmosphere. Otherwise, you just become untethered from reality. And this step is called the assimilation step of the weather forecasting pipeline. You update your forecast towards the observations. For those of you who know about Kalman filtering, this is exactly sort of the Kalman filtering type update equations that you use to compute this. I can talk more about this in questions if people have questions about this, but I'm going to stay high level for the minute. Once you've assimilated, you can forecast again several hours into the future to make predictions about what's going on, or 2 weeks into the future, and then you have to update as new measurements come in, and so on and so forth. We keep iterating this process. And then the final step of weather prediction is what you do with these estimates that come out of the forecasts. There is a small amount of post-processing that goes on in order to give you the sorts of predictions which arrive on your TV screens and your tablets or on your websites that you visit. Those post-processing involves a small amount of statistics to bias correct and slightly update the predictions that come out of the numerical systems. And you could view this as doing a little bit of machine learning on top of the numerical weather prediction forecasts, but it's a small amount of statistics or machine learning. Okay, so in this context, what did the papers from Huawei and DeepMind attack? Well, they have purely attacked this forecasting step. So when they say that these, NWP is going to be revolutionized by AI, at the moment, currently, it's only the forecasting step that has been sort of dramatically accelerated from AI. This assimilation step has not been touched, and one of the dirty secrets of the papers is that 50% of the compute goes into the assimilation step. So 50% of the compute is spent doing this, and 50% is doing on the forecast. So there still remains to be a lot of work to be done to how we could integrate this into the machine learning pipeline. And in fact, that's one of the topics that I'm really interested in my research group, but I won't talk much about that today. Okay. Great, okay, so that's the background about how things work. So in this context, why do we say that numerical weather prediction is very much the rabbit in the headlights of deep learning? Well, there are a few reasons, and I think here the field of weather prediction and climate has much to be commended for, because unlike many fields, they have done an amazing job of getting their data in great shape, ready to be attacked by things like AI, machine learning type methods. I'll use those two words interchangeably, by the way. Okay, so they have taken great care to produce extremely clean data sets, which are incredibly easy to access comparatively using software. There are no IP issues or limited IP issues. There's no privacy issues. If you think of something like health, which is crying out to have sort of machine learning thrown at it, there's often data cleanliness issues because the recording of the data hasn't been done particularly well. There's often missing data because people haven't bothered to fill out sort of key bits. There's often privacy issues, quite understandably, and so it's really hard to sort of get going. In comparison to that, the field of numerical weather prediction is just ripe to be attacked. It's like data ready, which is the first step for any field. Secondly, a forward pass through a neural network is much, much faster than simulating these big numerical weather prediction methods. We're going to replace this numerical simulation with applying a neural network. And that neural network, as I said, can be executed 1,000 to 10,000 times quicker. So there's big speed ups to be had. And perhaps even more importantly in the long term is that you can take this neural network and you can train it to predict things to do with actual observational measurements. So rather than just trying to emulate the numerical weather prediction system, you can actually get it to try and predict real observations directly, and you can optimize it to be better at it. And that will lead to further sort of accuracy gains. Another reason why it's ripe for attack for machine learning is there are loads of different types of data sets. I've talked about satellite data sets earlier on in the talk. I've also mentioned observational data sets like these radar measurements of precipitation that showed up on the nowcasting slide. But also there are climate simulators. There are climate simulators of different resolutions, some of which have a very fine-grained picture of the atmosphere. Others which show you what's going on in great detail at the surface. And machine learning allows these data sets to be combined. They can be brought together by machine learning. It acts as the glue for bringing them together and leveraging them all for weather prediction. And the final reason that I think that the field is ripe for machine learning is that if you look at these longer time scales, where I said it was important to return predictions with uncertainty around them, the way that people currently do that is they actually run lots of different models forward, lots of different numerical solvers with slightly different initial conditions and maybe slightly different models, and that gives us some set of predictions which encapsulates our uncertainty with what's going on. But of course, obviously, running what this is called an ensemble, running this ensemble takes loads and loads of compute because you have to run that same system multiple times, maybe 50 times if you're in ECMWF. And so there's an opportunity for a further speed up by a factor of 50 if you could use machine learning to actually replace the entire ensemble. And that's something that machine learning is well placed to do through the use of probabilistic methods and probability distributions. That's something which is central to machine learning. You might be familiar with generative AI that can generate images stochastically. Well, that same sort of techniques can be used to potentially accelerate whole ensembles of models together. But that's sort of very much in the future. Okay, great. So that's why it's a good place to deploy machine learning and why I think people are making progress quite quickly in this area compared to some of these other areas where eventually machine learning will have a big part to play. There are some major caveats, though, here. Reasons why you might expect machine learning not to be the go-to tool in this area. And so I want to sort of disclose some of them here as well. One major one is that we require these numerical weather the predictions of weather, to be good at the extremes. That's sort of the type of weather we're most interested in predicting in some sense. You know, storms, downbursts, hurricanes, fire, flood, etc., etc. And these are rare events. These are extreme events. And AI and machine learning perform really, really well when you have tons and tons of data. They don't tend to perform really well when you're in the tails of the distribution, when you're dealing with extreme events. And so there's a risk that these AI systems will fail catastrophically when we need them the most. And so you'll see that one of the things that DeepMind and Huawei have tried to do in their papers is try and evaluate these systems on extreme events and see how well they hold up. And at the moment, things look more promising than I would expect, but I still think we need to be sort of wary of this. What compounds this matter further is that the climate, of course, is changing. And as the climate changes, that means the models that we've trained will be out of date. They'll be trained on data which was appropriate when the climate was in a different state. And so it's not clear how machine learning is going to deal with that shift in the distribution of the data. And so there's a concern here, particularly about these extreme events in the context of climate change. Presumably, these systems will need to be retrained all the time in order to accurately take into account the effects of climate. Other things which make this super challenging is the size of the data. So if you think about machine learning on images or machine learning for text, things like ChatGPT, each data point might be about a megabyte, maybe a bit more, maybe 5 or 6 megabytes it's of an image. If it's text, it's a few hundred bytes or something like that. It's small, it's tiny. That is not the true for weather. For weather, we'll be seeing that each one of our data points, so each data point in the data set, is tens of gigabytes big. And that produces real challenges for using even the most basic machine learning systems in this space. Like the size of each one of the data points is vast. ChatGPT was changed on a huge data set, but each data point is comparatively small. This is doing machine learning in a completely different regime to what we're going to be talking about here. Great, okay, so that's some of the reasons why we might think the AI approach would have difficulties. There are others, but I'm happy to sort of speak to those in the questions. Okay, so let's now sort of set the scene for how DeepMind and Huawei actually applied machine learning to this problem. And here there are several ways we could have set things up. And I'm going to sort of talk through the way that they actually set things up in the context of the diagram I showed you about the way medium-term weather forecasting works. To set up any machine learning problem, you need to define two things. You need to define the inputs to the system. That's what we're going to be giving to our neural network, which I've called F here. And we also need to specify what the neural network is going to output. What's it actually going to predict? Okay? And perhaps the most obvious way to set this up would be to take this initial state of the atmosphere as input, and then to run a forecast using our expensive numerical weather prediction equations that were simulated on our supercomputer, and get the output here and just stick it into our neural net. So get the neural network to try and act as a surrogate for the numerical weather prediction model. And that would be really, really good because it would speed up this really expensive 40 pages time-stepped at 12 minutes. It would cause us to have 1,000 or 10,000 times speed up in the system, but it wouldn't be able to beat that system because it's just trying to emulate it. It's just a surrogate for the NWP. It can't be more accurate than the NWP because that is what it was sort of trained to emulate. And so a better thing to do is to remember that we've actually got these observations hanging around, And those observations allow us to refine this forecast through this assimilation process and give us an even better estimate for what the atmosphere is doing at that time point. And so you could use this as your target in your machine learning system. And this would now have the potential not just to be faster than numerical weather prediction, but also to be more accurate because you were sort of directly predicting something to do with the observations. This is not how things are set up because we can actually do something even smarter. And the even smarter thing is to use observations in the future to shape this estimate for what the atmosphere and surface variables are doing as well. This system is all going to be trained on historical data, so we don't need to be doing things in real time at training time. And there are products that the numerical weather prediction systems produce, which are used for evaluating numerical weather forecasts and are used for research, which assimilate observations into the future in order to refine estimates for the atmosphere and surface variables in the past. So if you know about the Kalman filter and Kalman smoothing, this is very much the Kalman smoothed estimates, or analogous to the Kalman smooth estimates for the atmosphere and the surface variables. So observations into the future, of course, constrain what the state of the atmosphere must have been in the past, and this process is going to use that information to shape it. We also have the advantage that because we're collecting processing this data offline, that late arriving data can also be brought in to better estimate the state of the atmosphere. So in particular, satellites that take a lot of time to get the data back off them and integrated with the forecasts. And often if you're trying to make forecasts quickly, say on an hourly basis, some of the satellite data just hasn't come in yet. And so if we instead back off and say we're going to just treat this as training data, we don't need it in real time, we can wait for all the observations to come in, you can again get sort of more accurate estimates for the state of the atmosphere and the surface variables. And this is what we're actually going to use for our data for training this system. This offline, smoothed data, this really represents the best information we have about the previous state of the atmosphere. Okay, everyone happy? That's what we're going to use for our outputs, and that's what we're going to train against. Okay, let me just take 30 seconds just to show you some of this data, and hopefully this video will work. So this is a video, I didn't produce it, produced by these guys up here, which shows you some of the training data that we're going to use for this. This is the smoothed best estimate of the atmosphere of the planet. It's called reanalysis data because you've revisited it and updated it. It's called Error 5. It operates on a grid box of about 30 kilometers. So each grid across the globe is going to be 30 kilometers big. It's updated every hour, and it also includes about 137 different levels through the atmosphere, different vertical levels through the atmosphere. And it's incredibly beautiful to look at. As I said, this is amazing data that the community has produced here. Let me just see, let me just hop it, not right to the end. Sorry, I got too many things going on here. Let me just show you some of the different variables in here. So this is variables to do with wind speed throughout the atmosphere. This is stuff to do with the humidity of air parcels through the atmosphere, how much water vapor content there is. There are other variables in here like temperature, pressures at different heights. Let me see if I can show you some other variables in here. This is the cloud cover at each point on the atmosphere, so on and so forth. So large numbers of variables, large numbers of grid points across the globe and through the atmosphere. And this is where you get to the point where you have gigabytes and gigabytes per data point here. Let me just show you this final variable type. So this is water type. Precipitation is another one of the variables which is in here. This is showing the sort of the liquid water content of clouds. Great. So this is the incredibly rich training data. Actually, both of these papers are going to use to train off. They're going to take a single snapshot of the globe, and they're going to look to predict what's happening an hour later, or maybe 6 hours later. Good. Okay. So that's the training data. And now we get to the tricky bit of the talk, where I'm going to explain, or attempt to explain to you, how we're going to actually carry out the predictions. So we're going to take that data as input at one time step, and then we're going to look to predict what that data would look like, say, an hour into the future. And one of the remarkable things about these papers is that they're going to use exactly the same techniques as are used in large language models. So let's take ChatGPT. We're going to use the same techniques that are used to generate realistic-looking text from prompts that ChatGPT uses, and we're going to throw in weather data without too much changes to that architecture and just cross our fingers and see whether it works. So I'm now going to try and explain to you in about 10 minutes how that technology works, and that technology is called a transformer. And there are no good explanations of transformers on the web, certainly for a layperson, so I'm going to attempt to come up with a half-decent explanation for you, and you can tell me whether I've succeeded or not. Okay, so this sort of system, this transformer, is going to take in a sequence of words. Here the sequence is numerical weather prediction is, and it's going to attempt to predict what this next word is. And I'm going to tell you how the system does this. It's going to convert each one of these words into a vector to start with, a collection of three numbers. It won't be 3 in the real system, it will be a bit larger than that, but here I'm using 3. And every word is going to have its own unique vector attached to it at the bottom here. So wherever is turns up, it will always be represented by these 3 numbers. And wherever prediction turns up, it will always be represented by these numbers, and so on and so forth. Those little vectors will be learned from the data. They'll be one of the things that we learned. Every word has a single unique representation in terms of these numbers. What's going to follow in the transformer is not going to be sensitive to the order in which these words appear. And so we're also going to need to add to these vectors some information about where those words appear in the sentence. And so we're going to append to the bottom here these numbers 1, 2, 3, and 4, which indicate where in the sentence each one of those words are going to appear. In reality, a few more numbers are used here, but this is sort of the general idea. We encode what words are present and where they're positioned in the sentence. Okay, so that's where we start, and these are going to form the inputs to our transformer. I should say in GPT, the T stands for transformer. GMP, a general purpose transformer. Okay, so the first step in the transformer after you've arranged your inputs is to do some processing across these features. We're going to call each one of these numbers a feature representing the word, and we're going to process each of these sets of features independently. And I'm not going to tell you much about how that processing takes place. Suffice to say, it's done by a standard neural network. So here you can plug in sort of neural network 101, and it will make some changes to each one of these vectors. And we'll process each one of them independently through the same network. So this has shaped the representation of each one of these words, but it has included no processing through the sentence at all. It's just done individual calculations on each one of the words independently. And so we now need a step which is going to collect information through the sentence, because in order to predict what this next word is, I need to know what the context of is was, what the set of words that preceded it, where did it appear in the sentence, in order to make the prediction for what comes next. And this is really the new bit that was inside a transformer that sort of unlocked these large language models, the way that this processing across the sequence proceeds. What you do in order to generate the new representation here, this eventually will become a representation of the word is in the context of what's preceded it. In order to generate this representation, we're going to do a really simple operation. It's surprisingly simple given how revolutionary this technique has been. We're just going to compute a weighted average of all of the vectors below it. Okay, so each one of these vectors, we're going to multiply by a number, and we're going to sum them all up, and that will give us our new vector is. And that will aggregate information from the sentence, because it now starts to depend on this word down here. This vector here will end up depending on the word numerical, because it's aggregated information across the sentence. And these weights here, these are all going to sum up to 1, so it really is a weighted average. And the way that the weights are generated is sort of the killer innovation in transformers. The way they're generated is by comparing the similarity of this vector to this one. It's computing the similarity between these two. That will give us these numbers in here. I won't give you the recipe, but it's actually a fairly simple recipe. And similarly, the number in here, the weight on this representation of the word weather, will be computed by measuring the similarity between these two vectors, and so on and so forth. And that then gives you your new representation of the word is. And we can do that for each one of these vectors in here by computing similarities here to get this one, and so on and so forth. Okay. So this is doing the processing across the sequence. These A's that I flashed up, let me just bring them back up. These A's have, as all things in machine learning, some jargon, annoying jargon associated with them. These are called attention coefficients. And so in a transformer, this thing is called self-attention because the attention weights are generated by the sequence itself here. They're coming from the same sequences with input to the system. Okay, it really is pretty much that simple, the way the cross-sequence processing works. You do that for all of the vectors coming into your system, and then you just repeat those two steps again. You do processing across features using standard neural network, the same for each one of our vectors here, and you do another processing across the sequence again, and you keep iterating backwards and forwards. In GPT-4, the most recent language model, you'd repeat those steps about 100 times, alternating processing across features and processing across the sequence. Okay, so when you've done that, say, 100 times, you then, at the top, get a representation which, once you've trained this system, and there'll be trainable weights in all of these boxes, the weights of the neural networks, and you have to train these representations of the words on the input side. Once you've done that, you can then use a simple classification system to output the probability of this next word, marked by a question mark. And this, again, would be a very standard piece of machine learning kit once you've got this vector at the top. And in this case, the system said, I think the next word with probability 0.6 is interesting. It's unlike GPT, it's a bit, it's rebelling against its masters and it's outputting boring here. Another one is computationally, and so on and so forth. For all of the words in your dictionary, you get a probability. And then you might pick the most probable one to fill in this question mark here, or you might sample them according to their probabilities. That's in fact what ChatGPT does. It samples the next word according to the probabilities coming out of the transformer. And in this case, by chance, we sample computationally. We then put that through the same transformer again. We recompute all of the vectors through the system, get a new representation for the word computationally in the context of what's come before it, and we can output the probability of the next word again and sample and so on and so forth. And that's how GPT, when you see it thinking, decodes sequences of text based on your prompts. Okay, that's how GPT works. All completely understand what's going on? Good. Laughter is usually conveys understanding, I think, or means you understand it very well. Okay, so this is the transformer, and the next question is, well, then how the hell do we use this for the type of data that we're seeing in weather forecasting? This feels like a completely different thing. Luckily, the computer vision field had already figured out how to port transformers over into vision and use them in tasks there. And so the strategy of Huawei was to just follow best practice in the computer vision literature, just treat this as a vision problem. And what they did was they took the data from error 5 that I just showed you with the big animation, and they unwrapped it to form an image. So they took all the data around the globe and they unwrapped it here to form an image of the surface variables, and took the pressure levels through the atmosphere, the information through the atmosphere, and turned it into a cube. And they did the same thing on the output side as well. These are the inputs, error 5 at one time point, and here's error 5 a few hours later. And we'll then take those unwrapped variables and we'll split them into little patches. So we'll just split the world here into 4 patches, and here we'll split the information through the atmosphere into 4 little cuboids, and we'll do the same on the output side and match up these variables. And now we can remove our words that we had down here and just take these patches and put them where the words were. So each one gets some pressure levels and some surface variables. And now these are what give rise to these numbers in here now. Before, these were learned vectors, one for each word. Now we can just take this data and use this to create these these numbers in these vectors on the input side. So we don't have to do any of these learning of vectors corresponding to each one of these tokens. We also have to include this position information because we need the system to know where this data comes from on the globe. And so this gets replaced by just the latitude and longitude coordinates of where those patches have come from. And we do the same thing on the output side at the top here. So for each one of the tokens, we take the surface variables and the pressure variables and we align it on the top in exactly the same way. And now we can train this thing to take in variables at one time point and predict what the variables would be at 1 hour in the future and train it a bit like a big curve fitting problem, essentially. It's like a regression problem or a curve fitting problem where you minimize, say, the squared error between what was actually observed and the predictions outputted by this big transformer, and that will give you your system where you can now go and deploy it to unseen data and see what kind of predictions it's making. And again, we can forecast multiple times in the future using this, what's called autoregressive processing, where we take the predictions and then feed them back in the inputs and then make another prediction and feed those back in the inputs to forecast multiple time steps into the future. Okay, that's how the machine learning works. Now, we've got through that. Now we can just look at the results in the last 10 minutes and see how well these systems perform. And I should say, I'm really happy to take questions about this. I know that was sort of a whirlwind effort to explain transformers in 10 minutes to you. Okay, so let's look at the evaluation. So the first thing I thought I'd do is just give you a feel for what the forecast looked like. And so at midnight on Monday last week, or the earliest hours of the morning on Tuesday, I went to the ECMWF website, and they've implemented Huawei's Pangu system on their website in an operational forecasting setting, and that let me forecast the weather for the entirety of last week through to today. Okay, so we're going to look at how well does this system predict today's weather. And this is the first forecast that it's given me. This is 6 hours after it was initialized at midnight, so it's 6 a.m. on Tuesday, and you can play along here. I'm going to make the first forecast actually through to Friday, and we'll have a look, see how well it's doing on Friday of last week, and then we'll forward it on to how well it's doing today. And I should say this is a plot of temperature shown on the colored axis here, and if you can't, this is the UK here, and Europe, and North Africa, and Middle East, and so on and so forth. Okay, so let's forecast forward. You can see we're getting nice predictions out. This is Thursday, and here we've got to Friday. Okay, so this is 6 a.m. on Friday. It's about 3 days and 6 hours since the system was initialized. And let's see how well this forecast matches up. This is ground truth on Friday, and you can see we'll match the pressure contours here that are coming out. The colors give you the temperature. If you look at the colors, they're pretty similar between the forecast and the ground truth, and the pressure levels are also pretty similar. So pretty good. After 3 days, the wheels haven't really fallen off. The prediction system looks pretty nice. Everything's pretty much predicting within 4 degrees C in terms of the temperature. Let's carry it on over the weekend. So we're into Saturday here. Saturday was quite hot and warm, and then things have cooled down again today. And here we're coming up to our lecture time, and we're here. So this is the forecast for what's going to happen right now at the start of the lecture, and this is what's come out as actual ground truth. I updated this just before the lecture, and you can see now there's significant differences. If you just look at the temperature fields, so the color map, you can see that's pretty similar. Not too bad. The pressures are a bit off, especially in regions up here, but perhaps not so bad. Okay, so this is a real machine learned system in action. Let's try and look at some results for the entire globe before I look more quantitatively at this. I'll show you some graphs in a minute. So this is a prediction for 3 days in the future based on the entire planet, and this is what ground truth looks like. If I flip backwards and forwards on this, you can see that one of the things the machine learning forecast doesn't do very well is it doesn't get high frequency information captured very well. They're all a bit spectrally washed out. They have too much low frequency information and not enough high frequency information, and that's something that needs to be fixed going forward. one of the limitations of the methods. This is the same thing for wind speed, not temperature. You can see in the Southern Ocean, after 3 days, there are some sort of fairly big errors in the Southern Ocean down here, but elsewhere perhaps not so bad. And again, you can see this tendency to get too few high-frequency components in the prediction. Okay, let's look at the evaluation. And one thing I should say is that the evaluation done in the original papers was flawed, both in the DeepMind paper and in the Huawei paper. They knew it was flawed, but it was very hard to do the real thing, and I can talk about why it was flawed. The plots I'm showing up here aren't flawed. They're an absolutely like-for-like comparison on an operational forecast. This was done by ECMWF, so it's a really fair comparison, unlike the original papers. So this shows results for summer 2022, and along the bottom here I've got how far we're predicting into the future, how many days, and on the side I'm showing you the error, the root mean squared error in degrees. So on average, how many degrees are you out on your prediction? This is the best numerical weather prediction system. This is the errors it gets, and of course the errors get larger as you try and predict further into the future. This is how Pangu does, the system from Huawei, and you can see up to about 3, 4, maybe 5 days in summer of 2022, it's about as good as the numerical weather prediction system. It's, remember, 10,000 times cheaper than NWP, so the fact that it's perhaps 1/10 of a degree worse at these long lead times perhaps is not so much of a surprise. Also note that, after a few days, the errors do become significant here, and that was in line with the sort of forecast that I made for today. After 7 days, the errors start to grow quite large, and were roughly 2 or 3 times as big after 3 days. Things on Friday looked quite good, and then things sort of fell apart over the weekend a little bit. The other dirty secret from the paper is actually state-of-the-art here isn't a single NWP model, it's one of these ensembles which runs forward and makes multiple predictions, and then you take the average of it. That's what this root mean squared error curve looks like, and it's substantially better than Pangu. So to say that it is going to reproduce the whole NWP pipeline at this stage is not quite correct. It's not really state-of-the-art if you take ensembles into account. And summer isn't a fluke. If you go and look at winter, you see a very similar story. In fact, Pangu is a bit better in winter than NWP in terms of accuracy, and this is because it's able to target this smoothed offline generated product called error 5, rather than just looking to emulate the numerical weather prediction system. Again, the ensemble is much better, so that's something, again, that's sort of swept under the rug a little bit in the papers. Okay, and I said we should look at extremes, and there's a couple of ways that they've done this. I'm just going to pick out one. They looked at typhoon forecasting. So they picked regions of time that had not been trained on, and they initialized it when hurricanes or typhoons had formed, and they made forecasts into the future, several days into the future, for what the weather would look like, and then they used some software to track the eye of those hurricanes, and that's what's plotted here. So black is ground truth, where these typhoons actually ended up, the trajectory that they followed. Red is the prediction of the eye of the typhoon from Pangu weather, and you can see in these two cases they're doing a good job of tracking these hurricanes, these extreme weather events where you'd hope these systems would do well. They haven't seen that many typhoons and hurricanes in the training data. The training data spans about 40 years, so they've only seen 40 years worth of typhoons and hurricanes, and they're quite rare. The comparison they did here to ECMWS product, ECMWS product went wrong in these two cases, but from the people I talked to on the inside here, they say that these are probably cherry-picked. In general, actually, when you do the comparison fairly, the two systems are about as good on hurricanes and typhoons. And I think that's actually surprising for the reasons that I laid out to start with, that I would not have expected these systems to be as good on these severe weather systems, but more checks need to be done here. Okay, so things are promising. I want to leave you in just the last minute with what next? Where's this going next? I think it's clear that AI is going to have a transformative effect in this space. It's not clear yet exactly which bits of the NWP pipeline it's going to replace. exactly how it's going to be integrated with numerical weather prediction, how it's going to deal with ensembles, how is it going to deal with the simulation. That's going to be a really interesting project that's going to take place over the next, say, 5-10 years. It's clear that ensembles are sort of one of the things that are next on the list, and using generative AI, things like diffusion to do this. This will also help us avoid this spectral bias problem where the predictions are over-smoothed. It will give us much more high-frequency information, and that will be really important. It will give us uncertainties in our forecasts. One thing that my group's been super interested in is this sort of dirty secret that 50% of the compute is spent on the assimilation. So really, we want to replace that with numerical methods as well. And in general, it would be great to have an end-to-end observations-to-observation system that we could just train in one go end-to-end. And I think that's something super exciting that will happen soon. And one final question is, where the hell did all the physics go? At the moment, there's very, very limited physics in this. I was a physicist as an undergraduate, and I find it a little bit sickening that the best way to get physics in this system at the moment is to just train on data that's come from a numerical weather prediction system itself. It isn't to build physics into the neural networks themselves. And I think that will have to change in the future. But for reasons that I'm happy to talk about in questions, it may be in the short term a bad idea. Okay, and that's 7 o'clock, and I will thank you for listening to me.